Related to spans is the idea of spanning sets. So we say that a set of vectors spans a set X if X is the span of those vectors. In this case, we're going to say that the set V1 through Vn, those vectors, is a spanning set for X. Now, note that spanning sets are not unique. So we saw before that P1 is the same as the span of X and 1, but it's also the same as the span of X and 2. So both of these, X and 1 and X and 2, are spanning sets for P1. So we say X1 is a spanning set for P1. This is how we would use this new terminology. So if we want to show that a subset of vectors is a spanning set for a vector space, it means we want to show that we can produce any vector, W, in that vector space using a linear combination of the vectors from our set that we're trying to show is a spanning set. The problem is that W often has infinitely many vectors, and so in order to check them all, we need to find an arbitrary vector and see if we can write that as the linear combination of the vectors that we have. So we're trying to find scalars so that this arbitrary vector can be represented as a linear combination of the vectors that we have. So let's kind of get some practice with doing these arbitrary representatives. If we're looking at R3, an arbitrary representative is going to be some A, B, C. If we want to look at P3, an arbitrary representative would be AX cubed plus BX squared plus CX plus D. Note that a spanning set needs to be a subset of X. So, for example, X1 and X squared cannot be a spanning set for P1, which is AX plus B, because X2 is not an element of P1. So we can't have X squared terms being used when we're trying to talk about just polynomials of degree at most 1. So let's say we're trying to find spanning sets for P1. So we want to find and figure out what AX plus B we can end up getting. What I'm going to recommend as we go through this part of the video is I'm going to show you a few examples of trying to determine whether or not different sets are going to be spanning sets. And when you think you have the idea, pause the video and try to determine it on your own. So if we looked at the set A, which is 201, what we're trying to figure out is, can I get any potential AX plus B to be equal to 200 plus times alpha 1 plus 1 times alpha 2. And so remember, when we're looking at polynomials, we're trying to use what's in front of the x as part of our system of equations, and we also want to determine the constant portion, how that fits into our system of equations. So here we get that A equals 0 and B equals 200 alpha 1 plus alpha 2. Now this is a little bit backwards from the way we normally write our systems. Remember, we can kind of go either way with our addition. So let's write this system. We have 0, 0, A, and we have 201 B. So note that this only works if A equals 0. Now when we're looking at polynomials, there are plenty of polynomials where the A part here is not 0. So we could have x plus 1, we could have 2x plus 3, we could have negative x, for example. So this is not going to be a spanning set for P1. Similarly, let's take a look at this set B here, which is just the set containing x. What we want to know is, can we take any AX plus B and represent it by some linear combination of this vector, so alpha 1 times x. Well, then this gives us that alpha 1 equals A, and 0 equals b. And so here we get a much smaller system. We get 1a, 0b. And so similar to before, this one will only work if b equals 0. So if the constant portion is 0. So overall, this set B is not going to be a spanning set for P1. All right, let's look at a few more examples. So let's say we wanted to look at C. C is x and x plus 1. So if we wanted to look at ax plus b and compare that to alpha 1x plus alpha 2 times x plus 1, what we end up getting is we want to know if ax plus b is equal to, if we distribute this through and combine like terms, we'll get alpha 1 plus alpha 2x plus alpha 2. And so our system of equations says alpha 1 plus alpha 2 equals a, and alpha 2 equals b. So then we get 1, 1a, 0, 1b as our matrix. And if we want to row reduce this, all we need to do is take row 1 and set it equal to row 1 minus row 2, and we'll end up getting 1, 0, a minus b, 0, 1, b. And so here, alpha 1 equals a minus b, and alpha 2 equals b. So no matter what a and b are, I can tell you what alpha 1 and alpha 2 will have to be. So since we obtained a solution C, that set above, is a spanning set for P1. So this one is yes. All right, now I don't want to go ahead and also work through and show you D and E, if only because I want to give you an opportunity to discuss them in the discussion boards. So discussion board opportunity. Are the sets D, which is x plus 1, 2x plus 2, and E, which is the set x, 1, 3x plus 4. So are those sets spanning sets for P1? If yes, explain how you know. If not, run off the page again. Explain why not. All right, so gives you an opportunity to get some practice with these, see how you're doing, and get a little bit of feedback in. All right, so we've seen some examples of determining whether or not some things are spanning sets or not spanning sets. So let's see a little bit more. So that was for polynomials. So let's say we wanted to show that R2 is spanned by both of these sets. So we're going to call this set A, and we'll call this set B. And so here we need an arbitrary vector to work with. I like xy. Reason I like that is it doesn't tie us down to any numbers for either of these. It could be any, X and Y could be anything at all. And we already have an A here and a B here, so I didn't want to call it like little a, little b. That might be confusing. All right, so let's show that A is a spanning set. In order to do that, we're saying that xy equals alpha 1 times 1, 0 plus alpha 2 times 0, 1. So if we combine those, that'll give us alpha 1, alpha 2 as a vector. Now when we compare real valued vectors, we're comparing each of the entries, the elements of those vectors to get our equations. So we get that alpha 1 equals x and alpha 2 equals y. We don't need to turn this into a matrix, but if we wanted to, it would be 1, 0, x, 0, 1, y, and we got a solution. So since we obtained a solution for alpha 1 and alpha 2, A is a spanning set. Does it seem straight up and down on the page to you? There we go. For P1. Okay, so that was pretty straightforward. Let's say we wanted to go ahead and use our set B. Well, then all we have to do is we'll set xy, our arbitrary vector, equal to alpha 1 times 1, 1 plus alpha 2 times 1, 2 plus alpha 3 times negative 1, 3. And so if we multiplied those through and combined, we get alpha 1 plus alpha 2 minus alpha 3 for the first entry. And for the second entry, we'll end up getting alpha 1 plus 2 alpha 2 plus 3 alpha 3 for the next entry. So here, what we'll end up with is the system of equations alpha 1 plus alpha 2 minus alpha 3 equals x, and alpha 1 plus 2 alpha 2 plus 3 alpha 3 equals y. And so this gives us a matrix of 1, 1, negative 1, x, and 1, 2, 3, y. And so here, we could go ahead and do our row operations by hand, but we have a calculator that'll do this for us. And so when we get into reduced row echelon form, which we'll use Octave Online and the sims command to use. I don't know if this is in this week's homework or last week's homework, but it is on there. We'll get 1, 0, negative 5, 2x minus y, and 0, 1, 4, y minus x. Notice here that there's no leading term for this column. So because this is a free variable, alpha 3 is free, we end up with infinitely many solutions. So going back over here, we can rewrite this to be alpha 1 equals 2x minus y plus 5 alpha 3. Alpha 2 equals y minus x minus 4 alpha 3, and alpha 3 equals alpha 3. So we got at least one solution. So since we obtained a solution, for alpha 1, alpha 2, and alpha 3, B is a spanning set for P1. Okay. So we got a little bit more practice in there with spanning sets. So note that in each of those examples, what we found is that the span of a set turned out to be a vector space. Well, it turns out this is always the case. And because it's always the case, what we're going to do is we have a new way of determining if a set is a vector space, and that's just to check if it can be written as the span of some vectors. So, for example, if we had P1, that's the set of all AX plus B, where A and B are real numbers, and that's just the span of 1 and X, which we could also rewrite to be the span of X and 1. So remember, we said that the span of vectors was the set of all linear combinations of those vectors. And so now what we need to do is recognize that we can go the other way as well. So if we have the set of a linear combination of these vectors, we can rewrite it as the span of those vectors. So this is great. However, we have to keep in mind that in order to do this rewriting, every single part of our set builder notation needs to have some sort of arbitrary variable here that we can go ahead and use in order to do this rewrite. So that way it is really the linear combination of those vectors. But notice here that when we look at this set S, which is V1 plus A V2, where A is in the real numbers, that this is not a vector space, because we have this restriction of V. So we can't write it as a span, so it's not going to end up being a vector space. If we looked at this one, if we looked at T, this has a restriction of 5. So this is not a vector space. But here, if we look at A, the set of all vectors A times V1 plus V2, where A is in the real numbers, this is going to be the span of V1 plus V2. So this is a restriction that we could work with. So as long as our restrictions end up allowing us to have our arbitrary coefficients here that we can use to multiply by our vectors, that's a restriction we can work with. When we have things that are unattached to these arbitrary coefficients, that's when we end up having something that won't be a vector space. So we want to show that alpha 0 plus, that A0 plus A1x, where A0 plus A1 is equal to 0, is a vector space by writing it as the span of vectors. So this is something we haven't quite seen before. So we're used to saying that our arbitrary constants here can just be in the real numbers. Here we have a restriction. So let's rewrite this to say that A0 equals negative A1. Well, if we do that, we can rewrite this set A0 plus A1x such that A0 plus A1 equals 0 as negative A1 plus A1x. And now that we don't have a restriction, we just say that A1 is an unrestricted thing in the real numbers. We'll then notice that we can factor out the A1 and get negative 1 plus x, where A1 is in the real numbers. And once we get to this point, this is our definition for the span of negative 1 plus x. Don't really need those parentheses there. Do need the squiggly brackets though. And so because we can write it as a span, I'm going to call it V, because we can write V as the span of one or more vectors a vector space. So I know we've thrown around a lot of terminology up until this point. So let's try to straighten it all out. So we say that the set of vectors v1 through vn spans a set v if v is the span of those vectors. We also say that that set is the spanning set, or is a spanning set rather, for v if v is in the span of those vectors. And finally, we're going to say that v is spanned by v1 through vn if v is the span of those vectors. All of these mean that if we have some little v in our set big V, then there are scalars alpha 1 through alpha n, so that little v equals alpha 1 times v1 plus alpha 2 times v2, all the way summed up through alpha n times vn.